Hello everyone, in this video I'd like to talk about the Key Stage 3 topic called moments and turning forces and explain exactly what a moment is and how we calculate them, and then talk about the law of moments. So to start this off, I'm going to draw a very basic seesaw kind of setup. So we'll put in here the middle part of our seesaw, not the best sketch but still. We'll put the seesaw in place and we'll have someone, imagine someone standing on one side of the seesaw. So this thing in red that I've drawn, this is our pivot, and we've got the sort of saw in place and somebody's just sitting on one end. Now that person, when they sit on that side, will apply a force. So they'll be applying a force downwards. That'll be their weight, if you like, because they have, that person has a mass, and because gravity is pulling them down, that will provide a force, and the force in this example will be a weight. Now, I've positioned that person very specifically a set distance away from the pivot. Now let's say that set distance is 5 meters. So it's a very, very big, in fact that seems quite a large seesaw, but let's just go with it. That's quite a big distance from the pivot. Now what a moment is, essentially, a moment is a turning force about a pivot. That's what a moment is defined as, a turning force about the pivot. So when this person sits on this seesaw, they would essentially turn almost like this. They would push the seesaw down in this direction. It would appear to be going in a sort of anti-clockwise movement. That turning force is what we call a moment. Now we can calculate, we can put a value to that moment using the formula: a moment is equal to force times the distance, and that's the distance to a pivot. So let's think of some units for this. A force would be measured in newtons. A distance could be measured in centimetres, or let's say in this example, meters. So the units for moments would be Newton meters or Newton centimetres, depending on which one of the two we used. So as an example, let's put an example here. Let's say we want to work out the moment. There's a force of 10 newtons being applied at the 5 metre gap. So let's say the person sitting on a seesaw at 5 metres from the pivot, 5 metres. Therefore, our moment would be 50 Newton meters. It's that simple. So that's how we work out moments, or these turning forces. You look at the force applied times by the distance from the pivot. Let's think of another example. In fact, I'll draw this up in the top corner. Let's think of an example of, so let's say I had, here's a piece of metal, let's say a random piece of metal, and in that metal I have a nut that I've got there. So I'm not going to draw all the nuts and bolts, but let's say there's a nut there and I want to unwind and take out that nut. So what I'm having to use is a spanner. This is my attempt at drawing a spanner here. So let's say I've got my spanner, shade it in, and I'm going to use my spanner to pull that nut out. So let's say I'm going to push or use this hammer and I'm going to push the spanner in that direction, so in an anti-clockwise direction. What we have here is a force that's being applied in this direction here. That's F, so we've got a force being applied pushing the spanner in that direction. We have from where we apply the force, let's imagine from here, to the nut. Now that would be our distance. So you can see we've set up a kind of moment here. We have a force being applied across a distance, and this nut here is acting like our pivot. So we need to think, how would we make our moment greater? How could we get that nut out easier? And it's really done by two things. It's increasing two things. We could either increase the force that we apply, so the moment would be greater, that turning force would be greater, or we increase the distance, because that would increase the value that we get for our moment. So we'll get a greater turning force. So for example, use a longer spanner. So apply a greater force or just use a longer spanner. And that would help us to get that nut out of that piece of metal. Okay, so what we've done is described what a moment or a turning force is. We've used two examples of the seesaw and the spanner. And we've defined a moment in terms of its equation as being a force times the distance to the pivot. Now what we need to do is think of balancing those moments. It's a really essential part of this topic. So what I'm going to do is just shrink the screen ever so slightly, move it up to this top corner. And I was going to draw one, but I think I'm going to struggle here. So instead I'm just going to insert a picture of a crane. Because what I want to do is finish this video by talking about balancing those moments. Because this is a really important question. Because if I wanted to balance that seesaw, for example, I would have to make sure that my value for a moment on, if I take an asterisk, put it over here, if I were to sit somebody up here and I want the seesaw to balance, I need to make sure that the force they apply and the distance they sit to the pivot would equal that of the person I had at the beginning on the left hand side. So we're going to talk about balancing those moments, or the law of moments, if you like. So let's take our crane here. Now we can see that this part there, that central part, that is going to act as our pivot. And you can see that there is, I mean, undeniably a longer portion of the crane here than there is here. So straight away we can see that on this example we've got two different distances. So the question that exam students often get is, how can the crane hold some kind of weight and yet not fall over? How is it remaining balanced? So let's imagine, let's take a weight. So from this cable, let's imagine that we've got a block here, and this block is, let's put a number on this. Let's say that is 20 newtons. Let's say that is pushing down with a force of 20 newtons. The distance from the pivot, let's say, is, again, let's just use 5 meters as an example. So this turning force, if you like, this moment turning this down, would be 20 times 5, force times the distance, which would be 100 Newton meters in this example. So that's our moment, that we've got 100 Newton meters. Now clearly that's going to make the crane fall to the right hand side, so we need to balance it. Let's say this distance here on the left is only 2 meters, so it's much, much shorter. So to balance that, we're going to need an equivalent weight on this side. So we can put a weight of, well, let's think this through. If we've got a moment of 100 Newton meters on the other side, we need an equivalent 100 Newton meters on this side. So let's do the maths. We have, if our moment is 100, because that's what we're trying to aim for on the left-hand side, this side where I'm just putting an asterisk. If we've got a moment of 100 Newton meters, and we need to work out F, what force we need to apply, times the distance, and the distance is 2. If we rearrange that, we get 100 divided by 2, which is 50. So 50 is the force we need. So if this red ball, if you like, had a force of 50 newtons, then this crane would be perfectly balanced. So if we think about the box that we're trying to lift over here, that's 20 newtons, so that's quite heavy. And it's 5 meters to the pivot, so we have a moment of 100 newton meters. But on the other side of the pivot, even though the distance is small at only 2 meters, we have a 50 newton weight pushing down. So our moment, if you like, our turning force is still on this side, 100 newton meters. So that's completely balanced. So the same principle you would use for the seesaw. If we wanted to balance that, we just need to put somebody wherever they sit on that seesaw, whatever distance or whatever force they happen to have, if we sit them at the right distance from the pivot, it will balance. So this video is just a little short intro to moments, turning forces, and the idea that the force times the distance to the pivot would create that turning force. Okay, hope all that helps.